compressor station is pumping that gas pressure up into a transmission pipeline. So we're building tens of thousands of miles of new pipeline every year. Quickly, because this is all a rush. The whole idea is to get as much oil and gas out of the ground in the U.S. as possible in the shortest period of time. I'm not here to talk about energy economics. I'll let you figure out why that might be necessary. But here is a graph that shows by decade in which a pipeline was constructed, the frequency with which accidents occur in the pipelines constructed in that decade. See that? Here's the decade of the 1920s. Here's the decade starting in 2010. In what decade is the frequency of accidents highest?
Recent.
With the newest pipelines.
Yeah.
What the hell is that all about? Why would the newest pipelines have more frequent accidents? Answer the question.
They're in a hurry.
They're in a hurry. Thank you. All right. Can't spend more time on all these impacts that are local. I want to get to the global impact that's affecting all of us. But I want to summarize what science says about all the impacts, all the local impacts. Another bar chart. So an organization that I helped found, it's called PSE, Physicians, Scientists, and Engineers for Healthy Energy, took upon itself a task back in 2014 to find, gather, collate, and archive as much of the published peer-reviewed literature as possible that we could find on all the possible impacts of unconventional oil and gas. We took that upon ourselves as a task, using modern techniques for searching for publications every day. Starting in early 2014, we run our program and we search all the databases that we have access to find all the papers that have been published and figure out whether those papers intersect any one of the impacts we've identified. We've identified 12 different categories of potential impacts. And here's what we found. In 2014, we searched backward in the peer-reviewed literature and found that in 2009, worldwide, there had been 7 peer-reviewed publications on the potential impacts of unconventional oil and gas development in all the possible impact areas, 7 papers. The number almost doubled by 2010, we found 6 more. And then, exponential growth. And now more or less flattening out, somewhere around 300 new peer-reviewed publications per year, asking the same questions. In this category of potential impact, is there an impact? Is it positive or is it negative? So, growing literature, but we now have a little over 1,700 publications in the archive. 3/4 of them have been published in the last 4 years. What did we know at the beginning of the revolution? What did we know 10 years into the revolution? What do we know now? A whole lot. So where is the required reading for the president, for Washington, D.C.,
Governor,
for the legislators in every capital of every state where they're trying to develop or not develop unconventional resources, for every locality, for every green organization, for every pro-oil and gas organization? Where's the required reading? And if you're not doing the required reading, you're not doing good science, and you're not going to be enacting good policy, because you're not basing your policy on good science.
Has someone tried to summarize all of this?
Yes. Thank you. So, what we try to do frequently is try to summarize in each category. Let me show you the categories. So I told you there are 12 of them: air quality, climate, community, ecology, economics, general health, infrastructure, regulation, seismicity, waste fluids, water quality, water usage. All 1,700 papers are assigned one or more of those categories. And so we decided, why don't we start reading certain categories, read all the papers in that category, and to some degree subjectively decide whether the paper says no impact, good impact, bad impact. Got it? So, 2 topics. Only time for 2 topics today. What does the current science say about human health impacts of unconventional oil and gas development? You survey all the literature in that particular topic, and you find out that 86% of the papers say there is either an indication or a causal proof that there is bad health impact. 14% say no measurable impact. There's not a single paper we've ever been able to find that says if you are living in an area where there's unconventional oil and gas development, you're healthier now than you were before we started. Air quality impacts. 83% bad, 17% indeterminate. No paper says your air is cleaner than it was before. Again, I'm going through this pretty quickly, but if you want to read it, if you want to read them yourself, there it is. There's your homework. Read 1,700 papers, or a couple hundred papers in the category that's of most concern to you. Last topic. How am I doing on time, Walter?
Okay, you have another 10 minutes before 20 minutes.
Perfect.
You're okay.
So last topic is going from local impacts or regional impacts to global impact, climate change. So how is the development of unconventional shale gas and oil related to climate change and related to renewable energy? Because today, 2019, we can't talk about any one of those three topics without intersecting, interacting, and colliding with the other. Unconventional oil and gas development, climate change, renewable energy. Don't talk to me about any other one unless you're willing to talk to me about the other two. They're closely coupled phenomena, which I'm going to try to prove to you. I'm an engineering professor, or at least retired engineering professor, so he never talks in philosophy. I have a PhD, I'm a doctor of philosophy, I have a right to talk about philosophy. It's the only thing I can cure. I have a friend at the University of North Texas, Adam Grimmel, who a few years ago published a book with an intriguing title, A Field Philosopher's Guide to Fracking. What he meant was hydraulic stimulation. He wanted to sell books, so he gave it the fracking title. What's a field philosopher? I didn't know what it was until I met him. He told me to read my book. Field philosophy is the philosophy as applied mathematics is to mathematics. Field philosophy is the pragmatic, practical application of philosophy in everyday life through the application of moral and ethical principles. Are there any moral and ethical principles involved in unconventional oil, gas, climate change, and renewable energy?
Doesn't seem like.
Okay. So in the first chapter of this book, which you're also assigned, so you're going to read 1,700 papers in one book so far. In the first chapter, he talks about a technological wager. A wager is a bet. Now, as engineers, fledgling engineers, scientists, we're familiar with what a technological wager really is. It's betting that at this point in time, we just invented something that had never existed, and we're going to try to use it. But we have better be careful, because usually associated with any new technology, there are unintended consequences. So, fracking, hydraulic stimulation, is an example of a technological wager by which we mean a gamble, or even a faith, that we can transform the world in pursuit of narrowly defined goals, and then, when the broader unintended consequences arise, we can manage them. We can manage climate change, right? It's the unintended consequence of the fossil fuel era. Anybody else think of an example of a technological wager that has some very important unintended consequences that are on the front page of every newspaper nowadays?
Genetic engineering.
Are there unintended consequences with the development of the technology called Facebook? Are we managing them? Wow, that's really difficult, isn't it? Or how about shale? Unconventional development of oil and gas and shale. All right, so let's see, what were the narrowly defined goals? You can read back in the literature starting in 2000. We're a Saudi Arabia of natural gas. We have enough natural gas and oil from shale to last us 100 years. We're gonna put thousands of Americans to work. It's gonna stimulate the GDP, it's gonna provide us with energy security, it's gonna lower prices for energy, and it's gonna help us displace dirty coal. Those are all good, right? And since shale gas and oil development has only happened in North America, taking into account the population of Canada and the United States, those narrowly defined goals are benefiting 5% of the world's population. Yeah, there are some shale gas wells in Argentina, even China, but 99.9% of all the shale gas and oil wells are in Canada and the U.S. 5% of the world's population theoretically is benefiting from that. What are the broader unintended consequences? I'm going to concentrate on these in the next 5 minutes. Exacerbation of climate change. That's certainly a broader unintended consequence. Prolongation of the fossil fuel era. Depression of renewable energy supply for everybody else on the face of the earth. Are there moral and ethical questions here? All right, so let's look at the first one, exacerbation of climate change. How do we know that the shale revolution of the last 20 years has made climate change worse? We know that because over the last 20 years, CO2 emissions worldwide, and especially in the U.S., have not decreased from what they were in 1990. In fact, CO2 emissions in 2018 in the United States are higher than they were in 1990. How many people here from 350? You got the wrong name. You should be 413. Okay. Yeah, okay. So, carbon dioxide concentration in the atmosphere is increasing at an increasing rate. We're now at 413, 414 parts per million. Okay, here's methane concentration in the atmosphere since about 1984. It was flattening out, and then somewhere in the 2005 to 2010 period, there's a kink in the curve. There's a kink. And now it's starting to increase at an increasing rate. Why is methane important? It's the second most important greenhouse gas emitted by human activity. And over a very short period of time, it's more important than carbon dioxide. Yeah, I said that. Over a short period of time, 5 to 10 years, methane emissions as greenhouse gases are more important than emissions of carbon dioxide. Because methane in the atmosphere, mass per mass, over a 10-year period is 100 times more potent as a global warming agent than CO2. A small amount of methane in the atmosphere has the same effect of 100 times that amount of CO2. That's science speaking, not me. How is that methane getting into the atmosphere from oil and gas operations? Methane leaks or is purposely emitted everywhere in the whole process, from the time you drill a shale gas or oil well to the time the product gets to your homes or to a power plant. It leaks or is purposely emitted in prodigious quantities. I'll show you a video of purposeful leaking. That is a legally mandated and legally permitted blowdown, excess pressure at a compressor station. That plume is methane, pure methane.
How long does it last? All the time?
That particular one lasts about an hour. I watched it. But all compressor stations blow down. Typically, they're required to do one blowdown per year to make sure all the emergency equipment works. And then they have periodic blowdowns when the equipment doesn't work. Same thing with pipelines. Every transmission pipeline by law has to be inspected. They pig them. Well, to pig a pipeline, you have to evacuate all the gas in the pipeline first, so you get the same thing. And I can go on and on and on. If you want to see more videos later, I'll show you more videos of all the places I've seen methane being purposely or accidentally emitted into the atmosphere. So we're still talking about impact on climate change. Next two slides are the most important for the rest of your lives. Whew. Crap, you sometimes are hyperbolic. All right, this is a chart taken directly out of a paper published in Science 7 years ago by a group of atmospheric scientists. It was an attempt at that time to show our global warming past and a projection of what might be our global warming future. So this is degrees of global warming. This is year. Whenever you say there has been a certain number of degrees of warming, you are required to say relative to when.
And whether it's Fahrenheit or
And whether it's Fahrenheit or centigrade. So this is centigrade, and the when here is we're taking 0 as the average global sea air temperature between the years 1890 and 1910. So you'll note the chart starts at 1900 and it starts at 0. And this black squiggly line is data, it's measurement. It's measured global, average global air sea temperature, measured periodically, actually daily, from 1900 all the way up to 2010. And by 2010, that temperature anomaly had gone to 0.7 of a degree centigrade. So when this paper was published, 0.7 of a degree centigrade, and at that point they used computer simulation, the best available software, best available science, the most powerful computers in the world, and dozens of different laboratories around the world in Monte Carlo simulation, and said under 4 different scenarios, what's our future? So each one of these colored lines is a prediction of your future in 2010. Purple line is reference. The basis there is whatever the emissions of carbon dioxide, methane, and black carbon is soot, whatever the emissions of those 3 anthropogenic greenhouse gases would be, they would continue at the same rate. And the computer model said, well, if that's true, we're going to pass 1.5 degrees centigrade in 2010, 20, 30, 2035. And we'll get to 2 degrees centigrade by 2042, which by your standards is tomorrow. By my standards, I'm dead. What do I care? I have kids and grandkids. I care. That's the reference case. Sort of the worst case scenario. Starting in 2010, we don't do anything to substantially reduce our emissions. Red curve. Suppose in 2010, we had started to drastically reduce CO2 emissions. Then the computer model said, basically no difference. I mean, there's a probability. These are the error bars, by the way. Let me show you what I mean by that. 95% confidence limits.
So they're at about 18 before 1.
Okay, good. So these are the confidence limits. For example, in the reference case, it could be, in the worst possible scenario, we're at 2 degrees centigrade by 2035. Best case scenario is we don't get to 2 degrees centigrade until 2075. Red is CO2 reduction, which we didn't do. Blue is reduce methane and black carbon, but don't do anything about CO2, and look at that. There's a delay. Doing something about CO2 in 2010 doesn't result in anything significant. Doing something about methane and black carbon results in something significant. We delay the inevitable by a decade or more. Buy ourselves some time. The best case scenario is in 2010, we had started to drastically reduce CO2, methane, and black carbon. And if you look at the error bars here, it would say, hey, there's a good chance we never get to 2 degrees centigrade. Good chance, 50% probability that we don't get to 2 degrees centigrade. Had we started a decade ago to do something significant? Did we?
Yeah.
Since 2010, there's 8 more data points put on that curve. Right? These simulations started in 2010. You want me to put the last 8 years of data up?
Yeah.
But it ain't.
Shit.
Oh, shucks.
Oh.
There's the last 8 data points. Last year was the 3rd warmest year. The year before was the second warmest year, 3 years ago was the warmest year. So the data points are falling on the reference curve or slightly above it. Because we didn't start doing anything in 2010, and we're still not doing anything significant on a worldwide basis. We just lost 10 years. And I would say we lost 20 years, because had we started back in 2010, bending this curve, and not allowed the shale revolution to occur. All right, prolongation of the fossil fuel era, I gotta warn you, the next couple of slides are gonna be kinky. In a calculus sense. You've seen this one before. Notice when this kink occurred. Somewhere between 2005 and 2010. What was happening then?
Economic meltdown.
Shale gas and shale oil were really taking off. Here's a plot, time versus total production in million cubic feet of natural gas in the United States. Look at that kink. Look one of the curves. Coincidence. Another kink. History of U.S. crude oil production. Look one of the curves. Coincidence. I'll show you another kinky curve in a minute. But you have to agree that what happened in the decade starting 2000 is that we prolonged the fossil fuel era. Look what was happening to natural gas production. It was on decline. Look what's happening to oil production. It was on decline. We kinked the curves up because of the shale revolution. Finally, depression of renewable energy supply.
Export.
In the United States, which practices capitalism, how can you outcompete your competition? What's the best way to outcompete your competition in a capitalist enterprise? Undercut their price.
Yeah.
Give them a product that they can use that's as an alternative to what you're trying to sell them, and give them that product at a lower price. Ready for another kink? History of natural gas price in the U.S. Notice this is not a linear scale. That is a least squares fit to that data. Look at that kink. Look one of the curves. We were paying $15 per 1,000 cubic feet of natural gas then. And as of yesterday, the price of natural gas in West Texas is negative. What does that mean? The company pays you to take it from you. The price of natural gas on the NYMEX exchange is about $2.15 per thousand. Nearly a factor of 10 lower than then. So communities all across the country, states all across the country, we're now faced with this dilemma of the price of natural gas being very low, the price of oil coming from $120 a barrel to as low as $28 a barrel in the last 10 years. And so do we build wind farms? Do we build solar farms? Do we heat our houses with heat pumps? Do we drive gasoline vehicles, or do we drive electric vehicles? All those decisions get impacted by pricing. So here's the plot of the history of U.S. wind energy capacity. How much wind energy can we produce in the U.S.? Here's the history. Up until about, oh God, here we are again, 2008, 2009. Something must have happened because there's a kink. We had exponential growth going on, and since then, the growth has been linear. That's bad. Here is a history of wind power generation in my state, New York. Up until that same period of time, exponential growth, and since then, linear or no growth at all. I proclaim, I declare, I submit that the kinks in those curves, renewable energy curves, are the direct result of the kinks you saw in all the fossil fuel supply and pricing curves. Okay, summary. Am I done?
12 minutes till 1.
Perfect. Let me tell you what I already told you. Fracking does not mean unconventional. Shale means unconventional. Fracking is as old as I am. Shale, oil, and gas are relatively new, roughly 20 years. Shale means scale in many different ways. Shale means intensity in many different ways. Scale and intensity apply more and different health and environmental impacts that are just now begun to be understood, documented, and quantified. Most important impacts are on climate change because they affect us all, and on the energy transition, which is necessary before 1.5 to 2 degrees centigrade limits are reached.